We are jumping right in today with QwenLong-L1.5, post-training recipe for long context reasoning and memory management.
Yep, a really significant paper from the Tungi lab at Alibaba Group.
And it really lays out a full blueprint for how you can take a 30 billion parameter model.
Which normally would struggle with really long contexts.
Right, and it catapults them into what is really state-of-the-art territory for long context reasoning.
Right.
We're talking about competing with models like GPT-4 and Gemini-1.5-Pro.
This is not just a small tweak, it's a complete post-training system. And the headline result is pretty wild.
I was shocked. It surpasses its own baseline by an average of almost 10 full points on long context benchmarks.
It's a huge leap, and they credit this to what they call their 3 pillars. The first one is, well, it's fundamental. A new long context data synthesis pipeline.
Okay, so moving beyond just needle in a haystack.
Exactly. They programmatically generate really challenging, verifiable, multi-hop reasoning tasks.
The second pillar, then, is tackling training instability. We all know reinforcement learning on long sequences is a nightmare.
So they developed stabilized RL. They introduce a couple of key methods like task balance sampling and something new called AEPO, adaptive entropy-controlled policy optimization.
And the third pillar, this is the really forward-looking one, a memory-augmented architecture.
Yeah, this is for the ultra-long context. Think 1 to 4 million tokens. It reframes the whole problem into a sequential decision-making process for an agent.
Okay, let's unpack all of that because it's a lot. I think we have to start with the data.
Always.
Because you can have the most brilliant model, but if you train it on simplistic, noisy data, you get nowhere.
Exactly. And the big gap they found is really a human bottleneck. I mean, think about it. How can a human annotator create, let alone verify, a complex question when the answer is spread across, say, 50,000 tokens of text?
It's impossible. You can't hold it all in your head.
You can't. So their main idea was to automate that complexity and, crucially, the verification.
How do you do that at scale?
They start by deconstructing huge documents into what they call atomic facts and relationships. Then they use those atoms to programmatically build complex questions.
So the model is forced to find evidence that's scattered all over the place.
Precisely. It has to aggregate bits and pieces from potentially dozens of different sections to form the answer.
And it looks like they built 3 different specialized generators for this. The first one is for in-depth multi-hop reasoning. This is the one guided by a knowledge graph.
That's the one. They use the underlying structure of the data, the relationships between things, to plot out a reasoning path for the question.
So they're literally using graph algorithms, like a random walk, to make sure the evidence is spread out.
Yes, and spread out very sparsely across different documents. But then they add a clever twist to make it even harder.
The perturbation and obfuscation. Tell me about entity obfuscation. Is that just swapping out a name for a description?
That's a great way to put it. So instead of asking, when was Alibaba's IPO, they might ask, in what financial quarter did the e-commerce giant founded by Jack Ma have its major stock market debut?
Ah, okay. So you're forcing the model to infer the entity first, then find the fact. It can't just keyword search.
Right. It requires a much deeper understanding of the document's actual content.
Okay, so then the second method handles numbers. This is the corpus-level numerical reasoning QA.
Yeah, and this is for things like financial reports, where generating verifiable math problems is really hard.
So what's the trick?
They built something called a structural tabular data engine. It parses all these unstructured documents, extracts a schema, and unifies everything into one giant structured table that spans all the source documents.
And then they just use NL2 SQL to query that table.
Exactly. They can simulate these really complex analytical queries, like calculate the quarter-over-quarter growth, and because it's running on a structured table, the ground truth answer is perfectly verifiable.
That's very clever. It ensures the data for benchmarks like DocMath is actually testing computational reasoning.
And the third method is more general. It uses that multi-agent self-evolve framework, MAC.
This is the model as generator approach, right?
It is. You have 3 agents, a proposer, a solver, and a verifier. The proposer generates a question, the solver tries to answer it, and the verifier checks it.
And the key is that it learns, right? The proposer sees which questions were good and which were bad, so it gets better.
It gets progressively harder. It's conditioned on a history of valid QA pairs, which pushes it to generate more diverse and more difficult questions over time. It stops it from just repeating itself.
So the scale they achieved here is pretty impressive. They went from, 1,600 samples to over 14,000.
And pushed the max length to almost 120,000 tokens. But you're right to be skeptical. With 14,000 samples, how do you make sure they're all high quality?
The verification bottleneck comes right back.
So they have two really crucial checks. First is the knowledge grounding check. They throw out any question that the model could just answer from its own internal knowledge.
So it has to use the provided context. It's actually testing its reading ability.
Exactly. And the second check is for contextual robustness. Here, they check if the answer is still correct, even after they've strategically inserted a bunch of irrelevant, distracting documents into the context.
Okay, that is a rigorous pipeline. So the data problem is, for the most part, solved. But that just leads to the next headache.
The training loop.
Why is reinforcement learning on these super long sequences so difficult?
It's a mix of computational cost and just raw instability. If you're using a standard algorithm like PPO, the advantage estimation step requires processing the entire sequence.
And with quadratic attention, that becomes impossible at 100,000 tokens.
Completely prohibitive. That's why their baseline model uses GRPO, Group Relative Policy Optimization, which is more efficient for long sequences. But even that has problems.
Why? What's the issue there?
The data itself, this new synthesized data, is it's not uniform. It's what they call multi-clustered. In one batch, you might get a bunch of simple dialogue tasks, and in the next, you get incredibly complex numerical reasoning.
Right. So random sampling creates these huge imbalances from one batch to the next.
And that causes the model's policy entropy to just spike and crash. It can lead to total training collapse.
So their solution is task-balanced sampling.
It's a simple but really effective idea. They just make sure that every single training batch has a balanced representation of all the different task types, multiple choice, multi-hop, numerical, and so on.
And that alone just smooths out the training process.
Massively. It gives the policy a much more stable view of the world it's trying to learn.
They also did something really interesting with how the model calculates the value of its actions, the advantage estimation.
Right. Normally, you'd normalize the rewards across the whole batch, but the reward distributions are totally different for different tasks.
A needle in a haystack task gives you a really strong, dense reward signal right away.
Whereas a multi-hop QA task might give you a very sparse signal only at the very end. If you mix them, the dense rewards just drown out the sparse ones.
So they isolate them. For each task, they only use the standard deviation of rewards from that same task within the batch to normalize.
Precisely. It gives a much cleaner, more accurate advantage estimate for each type of problem, which is vital for the really hard tasks.
Okay, this brings us to what I think is the core engineering insight here. The credit assignment problem. If a model generates 1,000 tokens of correct reasoning, but the final answer is wrong because of one bad step, how do you avoid punishing all the good steps?
That's the million-dollar question. And what they found is that for long context reasoning, the correct and incorrect answers look very similar.
They have a huge phrase-level overlap. I saw the number as like a Rougeal of 45% for doc math.
Exactly. Which means an incorrect final answer often contains a ton of correct intermediate reasoning, but standard GRPO punishes the whole trajectory equally.
And that just destabilizes everything because you're telling the model that all this good reasoning was actually bad.
Their key insight was seeing a correlation between high entropy tokens, the ones where the model is really uncertain, and these huge noisy gradients that were causing the instability.
Which led them to develop AEPO, the Adaptive Entropy-Controlled Policy Optimization Algorithm.
Right. And AEPO is essentially a dynamic regulator for the model's exploration. It works with a target entropy range.
So if the model gets too uncertain, too noisy, and the entropy goes too high,
AEPO steps in and masks all the training samples that had a negative reward. It basically tells the model, okay, you're exploring too wildly right now. Let's just ignore your mistakes for a moment and only learn from what you did right.
that seems counterintuitive. If you're ignoring mistakes, how do you learn?
It's temporary. It's to stabilize the policy first, because the flip side is also true. If the model becomes too certain, too confident, and its entropy drops too low,
then AEPO reintroduces the negative gradients.
right, it forces it to start exploring again to prevent it from collapsing into a solution that it's confident about but is actually wrong.
And this dynamic control gave them, what, another 3-point gain?
A 3.29-point gain, yeah. It's a huge deal for stability.
So let's talk about the ultimate ceiling, because even with all this, 120,000 tokens is still a hard limit. When you're talking about millions of tokens, This whole approach breaks down.
It does. You need an architectural shift. You can't just throw more compute at a single-pass attention mechanism.
So they redefine the problem entirely, from single-pass inference to a sequential decision-making process.
Enter the memory agent.
Which acts kind of like a human reader, right? Going through a huge book, taking notes, and summarizing as it goes.
That's a perfect analogy. The user's query gets broken down, and the huge document is fed to the agent in chunks. At each step, the agent reads a chunk, updates its internal summary, its memory state, and then, this is the critical part,
It generates a navigational plan.
it generates an explicit plan for what to look for in the next chunk. It's deciding, okay, based on what I just read, I now need to find information about X.
So it's actively folding this massive global context into a compact, evolving memory state.
And only when it thinks it has all the necessary information in its memory does it generate the final answer.
But they ran into a big problem here. Mixing the training for this agent with the regular full context training. It just didn't work.
No, it caused catastrophic forgetting. The skills were too different, so they had to use a multi-stage training pipeline.
First, they trained the standard 120K model as much as they could.
Through 3 stages of full context RL, yes. Then, completely separately, they trained a specialized expert, the Memory-RL agent, only on those ultra-long tasks.
And the final QwenLong-L1.5 is a fusion of those 2 separate experts.
Exactly. They used a model merging algorithm called SCE to combine the 2 capabilities into one unified model. And this approach worked brilliantly. They saw a 9.48-point gain over the basic agent baseline on those million-token tasks.
Okay, so the technical side is solved. But this always raises the big question for any specialized training. What about generalization?
Did they sacrifice the model's foundational knowledge to get this one superpower?
Right. And the answer seems to be a resounding no.
Not only no, but it seems to have helped. Performance on general benchmarks like MMLU-PRO was stable, so the stabilization methods clearly worked.
But the really exciting part is the transfer to other reasoning tasks.
Yes, big gains on really hard benchmarks. AME-25 saw a plus 3.65-point jump. GPQA Diamond gained almost a full point. It suggests that learning to integrate information over long distances just makes you a better thinker in general.
The AME 2025 case study they included was just a perfect illustration of this.
Oh, it's fantastic. The baseline model gets stuck, it tries a heuristic approach and just kind of spins its wheels.
But QwenLong-L1.5 does something different. It performs what they call a metacognitive check.
It literally stops and realizes its own reasoning is flawed. It sees a logical contradiction between its current answer and a constraint in the problem.
It's like it has an epiphany. It realizes its first assumption was wrong, throws it out, and completely switches strategies to complex algebraic synthesis.
And that leads it directly to the correct answer. That ability to self-correct, to recognize a dead-end path and pivot, that's a huge step towards more robust reasoning.
And for anyone listening, this has direct practical applications. The model also saw a massive gain on long MIML.
Over 15 points. Which confirms that these skills are directly transferable to things like maintaining coherent, long-running conversations.
So to wrap up, what does this all mean for you, the practitioner? I think QwenLong-L1.5 proves that the post-training recipe is just as important as the model's scale.
Absolutely. You don't necessarily need a 175 billion parameter model to get flagship performance if you have the right data synthesis, the right RL algorithms like AEPO, and the right architecture.
So where do they go from here? What's the future work?
2 big things. First, creating a closed-loop data flywheel. They want to use the new, improved QwenLong-L1.5 to generate its own training data, its own complex questions and reasoning paths.
A self-improving system.
Exactly. And second, they want to get even more granular with credit assignment, moving beyond rewarding a whole trajectory to true token-level credit assignment.
And maybe even using LLM-based rubric reward models for more subjective tasks.
Which would be a huge step forward.
So the big takeaway here seems to be that all these innovations, they suggest that improving a model's long context ability isn't just about a bigger memory. It fundamentally enhances its ability to integrate and maintain information.
It seems to boost its general high-level reasoning across the board.
Which leaves us with a really interesting final thought. If a model can truly master organizing and reasoning over, say, 4 million tokens of information, is that mastery just a proxy for what we would call advanced cognitive skill?